the walkthrough for tutorial 4 on using prior contradictory data. In this tutorial, we're going to walk through in Julia, the zero install, the Navability SDK version, which I've already opened up in the next tab over here. There's a separate welcome video that describes some of the application focus of this tutorial. We invite you to go have a look at that, and a separate getting started video. This example really dives into the idea of having prior information that you want to combine with new measurement and sensory information, and what to do when those things are contradictory. So we're going to base this tutorial on a production, manufacturing, construction type example, where we have some kind of robot. This could be a robot arm as a probe or a wheeled vehicle traveling around inside a anticipated area which is rectangular, and then there's an opening with a hinged door with the hinges on either side, and we're going to try and discover which way it's hinged. We're going to take the four corners as known affordances and the door, and we're going to have a contradiction around the door, and we're going to localize the vehicle relative to these bits of information. So how best to do that? And we're going to do this with a factor graph. There's previous tutorials show you more how to do that. All right, and then at the end, we're going to link out again to a prior construction example that we've done, where we have as designed versus as built contradictions. Right. So I'll refer to this as a room with a door, and the robot's traveling inside of it, and the affordances are the four corners and the door. So to get started, this is a Julia notebook or a Jupyter notebook. If your environment does not yet have the Navability SDK installed, you can install that with this. And let's get started by loading the packages. I'm running with Control-Enter. Bring in Navability SDK and a small helper function that we'll use to identify the contradiction later. So let's start by building a factor graph using the Navability SDK. So what this code is doing is there's an independent user, robot, and session ID listed over here. And that's how we're going to identify our sessions on the servers. There's some information about covariances that we're going to use, so specifically a prior distribution and then a dual distribution, which we'll see later. And these are covariance matrices, hence the square. So let's load that as well. Okay, so let's start building our factor graph. So we're going to upload variables, C0, 1, 2, 3. These are the four corners. The positions of the corners are 0, 0, 21, 2010, 0, 10, and it rotates through the four directions with a prior distribution as a covariance. So this is a normal distribution attached to a prior post 2, and we're adding this factor and variables, and then the factors are priors on each of these four corner variables. So we'll look at a picture of that in a moment. Similar for the door, we're adding two variables, prior door and prior dual, and a prior factor on each of those over here. So in the picture in the moment, that'll be a bit more clear. So we're just going to start a solve on this graph already in the background, and then let's have a look at what this factor graph looks like so far. So this is going to run a solve on the server. It's going to take a little bit of time, and then I'm going to open up on the Navability app what the factor graph looks like right now. So we're in the Navability app. We're inside the factor graph visualization. Here it is. And then we've got filters set up on the right-hand side here. We're guest at navability.io. That's a common login for everyone. We have a robot and a session ID that's unique to what we set up before. And here they are, the four corners, C0, C2, C1, C3, and the priors that are on them. That's these factors with the F and a unique identifier that travels with them. So these are the four corner affordances that we have, and the door, which we've so far uploaded as a variable for what we expect, door prior, and a variable door dual, actually the other way around, sorry. There you go. So this allows freedom in, as we get measurements later, to understand which way around the door is actually mounted. So we're going to, later the robot will see measurements against this, and we're going to localize relative to these four corner measurements as well. So let's go back and continue here. So the solve is completed, or do we expect it to have completed? So let's see a geometric visualization of that same info. So I'm clicking through to the Navability app again. Here we are. You can find that also in the hamburger menu, geometric map, and it's got the same filter set up as before. So here you go. Here's the rectangle. It's currently representing the parametric values, the mean of each of these variables, the PPEs. So we're able to actually show more of the belief underneath. So you can click the belief button, show belief, show particles, and I'll use clown colors just to identify. So these four corners are the rectangle, the room, and then the door in here. The two points lie on top of each other, but they have different orientations, 0 or minus pi, as potential hinge orientations for the system. Okay, so we've just had a look at the factor graph view and the geometric view inside that factor graph. Right. Let's have a look at a variable. So we can, from the system call, get variable on a client in the context. Give me the variable door prior. This is asynchronous, so fetch to wait on it, to block. And then our little helper function from before, the prior information that we assume is that the door affordance is hinged on the left. This is important, as we will see that potentially show a contradiction later. Now we add the robot. We're starting to add new measurements to the system. So up until now, everything has been prior information we've had access to. Now the robotic system is starting to take new measurements. So the robot's first position in the space, x0, we add that as a variable, and a pose2 variable again, so that's got a x, y, and theta freedom in it. And then we're going to do something new here, where when we add the factor, it's a rigid transform, a pose2 to pose2 rigid transform factor, where we've got the measurement information here, again as a normal distribution of -2, -2, 0 rotation. But here's the new interesting part. There's a multi-hypo keyword provided by the system, where we say that we have full confidence of the association to variable x0 for the first part of the factor, but then the second, what would be just a second variable, is now associated with 4 different variables in the factor. So here's a fractional confidence in association. So let's say a quarter each. In other words, the robot is measured with this value and confidence, a rigid transform to one of the corners, one of the 4 corners, and we don't know which of the 4 corners have been measured. So we add that variable to the system, and then that'll wait for completion just to make sure everything's up. Then we will solve, and while that is progressing, let's go have a look at what changed in the factor graph itself. So here you go. As before, we have the corners C0, C1, C2, C3. So those are the 4 corners of the system. But there's a new x0 where the robot is at. And then this factor is the one we just added, which is a rigid transform in spatial Euclidean 2 or pose2, pose2. But it has fractional likelihood of associating with any of those 4 variables over there. And we still have the 2-door the prior and the dual information hanging out, not yet cited by the robotic system. All right, let's have a look at the solve complete. We just got the toaster update. Let's go have a look at what that looks like geometrically. So we're going to go to the Navability app. Don't be confused by this. We're still drawing maximum points. What we actually want to see is the belief. So I'm clicking the show belief button twice, and clown colors just to differentiate. So actually x0, the mean, is landing between these 4 modes of the system, these 4 hypotheses. So I'm just going to take away the PPs for a moment. So this sort of teal color has 4 probability mass points. So that relative measurement that we got of 2, 2, 0 is shy of any one of the 4 corners that has a 25% chance of being at any one of them. So after the solve, we've recovered the robot is presently at any one of these 4 points. So we have 4 hypotheses or 4 modes in the solution, and the door variables are still just hanging out. All right. So as predicted, there are 4 separate modes in the posterior marginal estimate for x0. And we have also recovered the estimates for the corners, but those are pretty well constrained by the prior factors. Okay, the critical point here is that even though the factor graph does not have a unimodal solution, we are able to perform and solve the graph to recover the correct non-Gaussian marginal posterior result. So in contrast to Gaussian solvers, we have recovered a non-Gaussian result after the solve. That's a key point. All right, so let's say the robot moves on to position x1. So we're going to add a new variable x1, that's again a pose 2, and then we are getting firstly the odometry measurement from x0 to x1. So that's how far the robot travels. And then second, we also measure a corner again, one of the corner affordances, by some mechanism, whether it's a LiDAR or a contact, where the measurement's -2, -4, 0. And again, we're saying we don't know which of the 4 corners it associates with. Now, we're actually being a little lazy here, because there will be a reduction in possible modes, which we could have gone and calculated ourselves, engineered, and figured out what would have happened here. But we're lazy. We're just going to pass it off as multi-hypothesis to the solver and let the solver tell us what is happening. So we run a solve again. It's going to take just a little bit of time. Sorry, I should run that sooner. And then once that's done, let's have a look at what the map estimate produces. So while that's busy, let's go just look at the factor graph visualization again. So I'll just use this. And I'm going to just untangle it a little bit so we can actually see what's happening. So here's the first pose, x0. Here's the second pose of the robot, x1. Actually, there might be a better way to draw it. Let's do it this way. Let's put all the new measurements from the robot on the right-hand side and put all the prior stuff on the left here. It's just going to take a moment. Let's just untangle this slightly. So the door variables are still hanging out. I got a valid solution, but we're not using them yet. There you go. And then there's one more corner. All right, so I've reorganized this picture just a little bit. So the 4 corners are here on the left. There are 2 multi-hypothesis factors, and there are 2 robot poses from x0 to x1 with an odometry measurement between them, this one over here. Right? And you saw the solve complete. Now remember, the server is doing a lot of work, so it might take a little bit longer, but that's fine. So stuff we already know on the left. Actually, to be completely accurate, let's do it this way. So all the prior information that we brought to the party is on the left here, and then all the stuff we're going to measure is on the right, and these multi-hypothesis factors. So let's go have a look at that map measurement. Here it is. Show belief. And I'm just going to hide the BPEs, and I'll have to explain just a little bit of detail. So the 4 corners that we had before for x0, so just by color, so there you go, x0 is this teal color, has now reduced to only 2. So it's possible that the vehicle started out here or here, these 2 corners, and then traveled -2, -4, so it's down to here, or up to there. Black is the x1 variable. Oops, it's not what I wanted. The black is x1. So there are 2 hypotheses. The vehicle or the robot traveled here on the left or up here on the right. So we've gone from 4 modes down to 2. Let me close some of these. All the tabs. All right. So important, mode 1 starts at one location and drives up to x1, and there's a second mode that goes on the other side, as I just showed, and these are the precise values in the rectangle. All right, so the robot travels some more to position x2, so we add another variable. We have yet another odometry, but look, it drives quite far now. The distance is long, 1600, and then again we measure one of the corners. So we've got a rigid transform pose 2 from x2 up to one of the corners. We're lazy again, even though it should only associate with a smaller set than 4. We're asking the solver. We're just lazy. We're just saying it's any one of these 4. You solver, please figure it out. Right, run a solve, and while that solve is progressing, let's go have a look at what the graph did. So I'll quickly do the same as before. Put all the new measurements on the right here. So x0, these are the variables, the odometry factors between them. There's a multi-hypo, there's a multi-hypo. Alright, and then the corner affordances with priors that we had before. And the door. Oh, quick untangle here. Oops. There you go, so the door prior. We'll talk about this guy in a moment. So the four corners on the door is prior information that was brought in. And then we have 3 measurements to corner affordances from 3 different poses, but we don't know how they associate. So the poses are x0, 1, 2. The measurements to the corners, but we don't know how they associate to the prior known information. So the stuff on the right is new measurements made. Stuff on the left is information that we brought to the party. All right, I think the solve should be ready. Okay, and then just enable show belief again so we can see cloud colors. Okay, so we still have 2 modes. So we've driven from position x0, which is one of these teal colors, so either here on top left or bottom right, up to position x1, which is black. Oh, I'm just going to hide that for a moment. Black, which is over here, or on this side we drove up, and then this new very neon color, this sort of bright, what is that, green, neon green, that's x3. So the one hypothesis is x0, x1, all the way across the 1600 units traveled to this neon color. Well, the second mode is x0 down here, x1 in black, and then all the way over x2 over here on the left. So it's these 2 L shapes that sort of lie against each other. So we still have 2 hypotheses or 2 modes in the solution after a solve. So that's pretty exciting. All right, we find there are still 2 modes in the posterior beliefs from x0, 1, 2, which represent 2 hypotheses that the robot is moving relative to the rectangular affordance. So note that we're localizing the vehicle relative to the affordances we had, so it's a fully relative system. It's not an absolute measurement structure. All right, the robot senses the door. So for the first time. So the last measurement made by the robot is to the door affordance, which is sensed by it as 2 units ahead of the robot, and a relative orientation to x2 being pi radians, 180 degrees. So the way in which the robot senses the door is not just the separation of 2 units, but also the orientation of the door as sensed by the robot. So let's start that up. I'll sort of maybe start the solve a little ahead. So here we have it. So we're adding just a factor from x2 to either door prior or door dual as a multi-hypothesis 50-50 split. Right, so look at this carefully. So it's again a rigid transform factor, which usually just goes between 2 variables, but now it goes between 3 variables, from x2 to one of the door variables. Prior, what we expect to find, and some freedom, door dual, maybe not. We'll see what gets measured. And then the measurement is 2 units ahead in x and pi rotation with some confidence. Not the most stringent confidence, but there it is. All right. How did the graph structure change while the solve is crunching? Okay, so now everything is connected. So door dual that we've had before, I'll actually put him out over here. Door prior, so this is stuff we knew in the past. Pose x2. Wow, this is a bit of a tangle to explain, but I think it's worth it to quickly do the effort. See corner 3, pose 0, here's corner 2, and it's prior. So again, prior information that was brought is here on the left, including the door, so 5 priors. And then the new measurements here on the right hand side from poses x0, x1, x2. So localizing the robot had 3 multi-hypothesis factors to the corner affordances. And then something extra happened where we had yet another multi-hypothesis factor which measured the door. And what's coming into play now is the use of this door dual. I didn't call it out earlier strongly, but the confidence on door dual, this prior, it's very weak confidence on the orientation. So that's kind of free to spin anyway, and the position is looser. So let's go have a look at what that does. Whoops. In the map. Oh, that's not the one I want. Almost there. There we go. So X2 has dropped down to just one mode, X1, one mode, X0 still has a little bit of excess modality here. I'm actually just going to start another solve in the background just to show that we do converge to a stable solution. And I'll talk through this in the meantime. So the most likely outcome is that the vehicle or the robot traveled from X0 here in purple down to yellow, X1, over to X2 in green over here. And then currently we have a filter set up for just show the variables that start with X. Let's redraw this without that. There you go. So the door variables over here, here are the four corners. So I can put those on. So there's C3, C0, C1, and C2. And the positions of the robot. So the mean is landing in the middle here. On second solve, you'll see it clean up to just 3 clean modes. Let's wait for that to quickly finish. We'll see that finish. We don't have a wait in here. No. That's what we were just looking at. Just give it a moment for the solve to finish. There you go. So X0, X1, X2, and the door right here. And you'll see the confidence for the door is actually tightened up a little bit. So there's our rectangle from our original picture. Let's actually go to where our picture is. If you remember this picture, there are the four corners and the door on the right here. There you go. X0, X1, X2, and the door inside the four corners. So we've resolved down from 4 different modes with relative measurements only, a unimodal solution using multi-hypothesis factors. And we've shown how the robot moves inside this prior known rectangular object. This measurement was made, or the solution was done with local measurements only, so not a global measurement. It's not like we set up a metrology system and measured globally. We just measured relative to the prior information we had. Okay, and let's have a look. If we compare the door prior with the door dual variables, we find that door affordance prior was left-hinged, but was resolved as right-hinged. So that's a very important point. So if I go into just the factor graph picture we had before, door prior it was assumed left-hinged, and we found that door dual was actually right-hinged. So this was resolved as contradictory to what we had in the map before. So we get that by looking at the PPE values for the variable. So we go look at door prior, pull out the PPE and print it, and then the same for door dual, and look at the parametric point estimate for that, and our helper function resolves it as left and right hinged. So we have a stable solution down to unimodal, which we uncovered a contradiction, and we resolved ourselves against prior information with relative measurements only. So we describe this idea of navigation affordances in more detail. I invite you to have a look at the navability construction example. Please do see that. And there's actually a paper that describes this in much more detail. I'll click through in a moment. And just to summarize, we've brought prior information together with new measurement information. We're expecting contradictions might happen. We found contradictions. The system was able to detect that contradiction, and a stable solution was held throughout. And whenever multimodality did occur, the system recovered that by itself. So this technique of multi-hypothesis can be used with any of the other non-Gaussian techniques described in earlier tutorials. All of this happened on manifold, so you can go have a look at how the manifold operations are done. There's a documentation there. Let's maybe do that one first. Here you go. So this is in the solver, CZL, which is open source. Here's a write-up on manifolds, which you may find interesting and useful. The solutions are done on the Bayes tree. But more importantly, let's go have a look at the construction example. So this is going out to Navability. Here's a robot that's used this technique in the wild, where it would measure in a room and against fiducial markers what you're expecting, where you're expecting to find them and where you actually find them, right? And then the idea of an as designed versus as built. So here is a floor plan example for the robot. Cyan here is as designed, and red is what was as built, but it was only detected by the measurement system afterwards. And this multi-hypothesis nature gets resolved, so here a contradiction is found where as built versus as designed don't line up. So we invite you to have a look at the paper. Here it is, you can find it, or get in touch for more information. Thank you very much, and please do see our other tutorials as well.